Hello everybody. Today in this talk, what I want to talk about is how we can analyze advanced and evasive Android malwares which employing some challenges. Recently, app analysis and app protection techniques are very improved, so recent Android malwares are employing some techniques to impede analysis. This slide shows that what challenges there are. From fast code analysis to environment detection, there are various challenges. So now I will introduce some effective techniques we devised to analyze evasive Android malwares while getting over these challenges. To prove the effectiveness of the techniques, we built a tool. This tool can work on the emulator and modify the Android image and even on nothing changed phone correctly. And it doesn't require root privilege, but a lot of existing tools are requiring it. Of course, if you have a root privilege, you can use some functions in more convenient way, but there is no problem if you don't have root privilege. Also, this tool can monitor not only specific behaviors of target Android application selectively, such as file activities, network activities, but also user-defined functions and even behaviors in native layer. This feature is very effective in native analysis of Android app. The key technique in this tool is flow-centric code analysis. Briefly, we implemented a tracer. In PC, there are several efforts to trace execution of user-defined functions and each argument. But it is not easy because the file format like ELF and PE didn't provide sufficient information about each function and arguments. Whereas DAVI executable format in Android provides rich information to trace execution of user-defined method, and each argument, because DAVI virtual machine needs a lot of information to execute a DEX file due to the structure characteristics of DBM. For example, DEX format exports method arguments, class structure, and external method information that is invoked inside of the classes of DEX file. And then DBM is supporting JDWP. JDWP is a Java debug wired protocol. It is used to debug Android application. When we implement flow-centric code analysis as a tool, the JDWP was excellent tracer engine. With JDWP, you can do getting symbol information, tracking class object, getting code stack, getting method execution flow. So we can know various and details about execution information dynamically, and even Android runtime in Android Lollipop is also supporting JDWP. And also, we can trace execution of user-defined method and various third-party libraries such as custom cryptography, custom network. And we are analyzing code stack to analyze correlations between code methods. With hierarchical structure analysis of a code stack, you can trace protected code by some obfuscation techniques such as string encryption, method invocation hiding, and class encryption. Many commercial protectors for Android application are using these obfuscation techniques to protect the app's code. And also, I'm going to tell later that you can get over against dynamic loading attempt and anti-analysis techniques with DEX injection technique. From now, I'm going to trace behaviors of evasive Android malware with some real malicious sample that is discovered in South Korea. This code steals user-sensitive information such as phone number, MAC address, IP address, and it sends these information to hacker server to inform infection. If you see this snippet, first it creates a Java object and put corrected information into JSON object with put method. This slide shows analyzed log of the snippet. As you can see, all code flow is the same with code in previous slide. So you can analyze code very fastly, as you can see. It is same. Next is about string encryption. String encryption is a well-known technique for Android code protection. This is also supported by most of Android app protection tools. String encryption makes almost strings in code encrypted strings. These snippets in slide are disassembly and decompiled code of an example protected by string encryption of DexGuard. The red line box area in slide highlights code line, which is calling decryption method. In some cases, this form of obfuscation can be analyzed easily because logic of string decryption method is simple, but recent logic of decryption method are complex, and so it takes a lot of time to analyze the logic statically. Now, again, let me analyze the string encryption example with flow-centric analysis. Generally, obfuscation techniques are solved by dynamic analysis. In our approach, the string obfuscation is solved by tracking string object. A combination of tracking creation of string object and code stack analysis can help static analysis, because we can see where string decryption method is invoked by analyzing code stack. Code position in code stack is useful for static analysis. In other words, you can analyze the code protected by string encryption with static analysis tools like JEB. And we can also get string decrypted through tracking members variables of the string object. In case of this example, the decrypted string was hello world. Almost the string encryption techniques can be analyzed with this approach, and we can selectively trace all methods we want to monitor. So even if string obfuscation decrypts encrypted string in native layer, we can see decrypted string easily because it has to create string object anyway. And this example for method invocation hiding. This obfuscation technique is also very well known and used frequently to hide method invocation. If the app is protected by this obfuscation, we cannot see what method is invoked. So this is one of the big hurdles for Android analysis of app. Normally, method invocation hiding is implemented combination of string encryption and Java reflection. First of all, it has to decryption encrypted string and invokes Java reflection APIs with decrypted string to invoke hidden method. So if we can trace string decryption and Java reflection APIs, it's going to be solved very easily. This picture shows some logs about Java reflection APIs. It is same thing with snippet in previous slide. If you see a red line box area, load class method of Darby system text file class is invoked to load the specific class from some text file. And you can also see that open the text file is located in its package private directory. It means that it tries to load some classes from dynamic loaded text file. So as you can see, that method invocation hide could be solved easily by flow-centric analysis. Moreover, this approach can help static analysis, as I mentioned before. So we can analyze this obfuscation statically with these logs. Therefore, we can understand the behaviors of obfuscated code in more detail. Now, I'm going to analyze a temper detection sample of DexGuard. This sample does some temper detection behaviors, and it is obfuscated using string encryption, class encryption, and method invocation hiding of DexGuard. This snippet is a part of temper detection sample. If you see this, you can see all method is hidden by obfuscation. By the way, if you see the code with this log, you can obviously distinguish behaviors of the code. This sample loaded the text file twice dynamically, and this means that it decrypts encrypted class and loads the class. And then it performs self-integrity checking. If you see the integrity checking routine, it is calling method with Java reflection. And if you see the each entries of logs, the sampler first gets a path of each APK file using get package code path API. And then it opens the APK file and gets a length of the file. After that, it created a CRC32 object. In this object, in this point, you can predict that it calculates CRC of each APK file and compare it with prepared CRC value. Therefore, you can know the temper detection sample of DexGuard checks APK file integrity using calculation of CRC. It is easy. And this is also checking certification. It is calling all related methods using Java reflection. If you see the logs, first it tries to get package info object from package manager, and then it gets a signature object from package info object. And it tries to get a byte array for signature value and then compare it with prepared byte buffer object using equals method. As you can know, now we can analyze obfuscated code and packed application with this approach, and Android platform is suitable to implement the flow-centric analysis approach. And now I'm going to talk about dynamic code loading. We can implement dynamic code loading in two ways. First way is that you can use related APIs or exported functions of libdbm. And second way is that you can patch partial contents of already loaded DEX in memory. Almost Android protectors are using these two ways to utilize dynamic code loading. First of all, if you have analyzed the DBM, you can know that there are some functions and methods related to dynamic text loading on both of Java layer and native layer. If you analyze a hierarchical correlation between these functions and methods, you can know that these functions are calling some functions after all. So therefore, if we hook the functions, you can get a specific point of time when it tries to load text file dynamically. With the hooking approach, you can intervene in execution flow by hook handler and get meaningful information using JDWP command and custom command implemented in injected text module. Injected text module have a privilege of a target app, so it can do anything what app process can do. So when our tool detects dynamic loading attempts, the tool dumps the text file to disk. Next is about patch type dynamic loading technique. This technique patches a particular area of already loaded text on memory using native library. Normally, text image area is in memory is a read-only area, so protectors that are using dynamic patch needs to get a write permission for a memory area which it tries to patch. And to getting write permission, they invoke mProtect function. So our tool intercepts mProtect function, and hook handler handles a request for a memory permission, and it returns success value for a request for write permission, but it actually doesn't apply write permission. Therefore, code patch routine tries to patch certain contents of text in memory, and in that time, segmentation fault will raise, and then our signal handler handles the signal and extracts some useful information, instruction address that causes the signal, and access memory address and thread context. With these informations, we can see that what contents that is patched and which code tried to patch and which thread did it. This slide, we don't have time enough, so I think I have to skip it. And this slide is about monitoring extension. Our analysis approach is using monitoring extension that is using text injection technique. It means actually just plug-in framework using text injection. Text injection is already well-known technique. To build monitoring extension system, we implemented custom command system, so combination of JDWP and text injection. With JDWP, you can send the command to injected module and receive results of the command. This is like a dynamic JDWP extension. With the monitoring extension, you can do anything which a process can do with your creative. For example, you can correct and monitor some information inside of app process, or you can explore package private directory without external support. I had presented a unpacking method for Android application at Black Hat Asia 2015, and that technique also used monitoring extension. Now, we had developed various special functions like anti-analysis, file extraction, and various detection using monitoring extension. And next is about native code tracing. From now, my colleague, Yeongung Choi, will talk about it.
Malware or packet code is written in native for hiding important codes. Java code is easy to analyze, but the native code is hard to analyze. Let's see fake Kakao for example. This is one of the malware sample using native code. You can find this sample at virus bulletin. In the beginning of onCreate method, you can see function called setJNI-env, handle onCreate, and readDat. But there is no information that could identify function. Just you can see a native keyword. Looking at the export table for the analysis of the actual code, you can see readDat and setJNI-env function. Where is on handle onCreate? You have to work hard for finding handle onCreate function. It is also difficult to find a Java method in native code. With this encrypted string, it's more difficult to analyze. In order to analyze combined Java and native code, we are tracking three layers: JNI, LIBC, and binder. JNI means Java native interface. If you can monitor JNI, you can know a native function called from a Java code or a Java method called from a native code. LIBC is a standard library provides functions for tasks like string handling, mathematical computation, I/O processing, memory allocation, and several other operating system services. If you can monitor LIBC, you can know what to do in a native code. Binder is communication mechanism of Android process. So if you can monitor a binder, you can know a communication data between app and service. Now I'll say how to track a native behavior. First, when a Java method call a native function, Darby virtual machine executed a dvm call JNI method function. dvm call JNI method get arguments, result value, and method structure as parameter. The method structure has a native function name and address that is called by Java. And dvm call JNI method is used for calling all native functions, so filtering is needed to trace the specific function. In order to call a Java method in a native function, JNI env structure is required. JNI env structure has a function table to call a Java method. The name is JNI native interface structure. The function table looks like this. If you change this function table, you can hook the Java method called by the native function. For changing this function table, I hooked dvm platform invoke function. dvm platform invoke function get JNI env structure as parameter. So you can change a JNI native interface. This is a tracking result of fake KakaoTalk app in JNI layer. At first, setJNI env function is executed. setJNI env function didn't call any Java method. Second, handle-on create call many Java methods and call register receiver, register content observer, and so on. Looking at the used method, you can see this app access contract and register memory receiver. In addition, the memory address of a handle-on create is displayed. This address is extracted from method structure at dvm call JNI method function. If you calculate an address on the file, you can easily find the actual code such as right side. At last, readdh function is executed. readdh call get device ID, get line number. So you can know readdh function get device information. And this is tracking result of LIBC. Many tools have ability to monitor LIBC, but that's all. If you combine the result of monitoring JNI and LIBC, you can see exactly what function should do. Here you can see lambda 1, line 2 string, open KakaoTalk plus APK and other functions. So you can think readdh has encrypting or decrypting routine and access their own APK for some reason. Finally, let's look at binder. I said binder is communication mechanism of Android process. This diagram shows how to actual communication is made. If you want to call B and foo services foo method, you can call foo provided by service proxy. Then foo call, transact and talk with driver I/O control. Bind driver look for foo service server and passes the data, and it goes up to foo method. There are many ways to track this bind communication. I/O control, transact, and foo. I'm not hooking I/O control function because it is also used for other purpose than service. The hooking service proxy like foo is not easy because every app uses different proxy function name. So I choose the IPC layer. It is easy to obtain and manipulate communication data because all communication service using transact, so we can monitor custom service. In addition, there are no performance issues due to track only services. When hooking transact at BP binder and B binder, you can see all the sent and received messages between target app and service or other app deeply. This is a tracking result of recording app. The tag means this data is sending to server or receiving from server. At first line, the app asks to mute the microphone for audio finger service. Audio finger service has sent the client that earphone pig was changed. The app asks to set voice volume. You can now detail the data from parser. Parser contains service name, data, and so on. Reply means return value of RPC. When an app uses a GPS service, you can see a GPS data as reply data or receive data. It is depending on where the GPS service to use. Service code description is extracted from AIDL object. Tracking binder is additionally also possible data manipulation. For example, malicious app obtain a video or photo with camera, tap with mic, and trace the position with GPS. At this time, manipulate the data transmitted through the binder. It is possible to protect the analysis information, just like change FD for storing a video, change sample rate to 1 for recording voice, change GPS data, and so on. Also, you can change device information, phone number, IMEI, SIM share. This is easy if you use an emulator, but remember, we use a real phone. Now, demonstrating our tool.
Let me show you a demo. This is the tool we built it. First of all, open a target applications APK file. This target is protected by text protector, and if you see it is with JB. You can see that there is no original code, and it may be each class encryption, and this code is obfuscated by multiple obfuscation technique. This is string encryption, and this is method implication hiding. So when you analyze this code, it will take a lot of time. So I'm gonna analyze this code with our tool. Open APK file. And select the trace point you want to monitor, and enable monitoring extension flag. This monitoring extension flag is for detection of dynamic loading and file extraction, and automatic install. And this point is nothing changed point. Okay. And launch. After launch, this tool generates a new debuggable APK file with the repackaging. So it will install and launch the application automatically. So you don't need to do anything after launch. And this alarm dialog is about dynamic detection of dynamic loading. So if you click this button, you can extract the text file into your disk. I will store it. And loading additional text file, and again select the trace point you want to monitor. And in this state, the app process in device is suspended. So if I click this button, the app will be resumed. And encryptable lock method is called very frequently, so I skip it. And unpacking routine try to load additional text again, so I will store it again. In this time, if you see that extracted text file with the hex editor, this is not correct text file, right? There is no magic of text file, text format. It's because this. After first text load text method, it calls unpack method. In unpack method, hashcode method in signature class is called. It's a very suspicious point. If you see this code in JEV, you can see that there is no protection like obfuscation. This is unpack method, and hashcode method is here. V7 has hashcode value. V7, if you see flow of V7's flow, see V7, 10, hashcode value is used in decrypt method, and in decrypt method, it passes it to encryptable long method. Encryptable long method is using it in multiple arithmetic operation. So, according to test protector's manual, test protector uses dynamic key for decryption. And in this point, you can realize that hash code value is a factor of dynamic key of test protector. So, our tool do repackaging. So, hash code value is different from original one. So, if we can modify this value, you can get completely unpacked text in this point. You can modify hash code value using Java method hooking technique. Java method hooking technique is very well-known technique, and you can get related code on internet, and it is open source. So, so far we examined text protectors unpacking routine, and now you can make text protectors unpacker.
Yeah, we have no time, so we skip demo native code. And conclusion, we tell about problems and how to solve. So our goal is how to analyze app easily, quickly, and deeply. So this is DeepERENT. Thank you for listening.